Have you ever wondered what kind of software is running behind the scenes on the most intense systems on the planet? I'm talking about financial markets that move faster than a lightning strike, or the flight control system on the plane you're flying in. These are worlds built on C++.
So, that brings us to the big question, right? How do you actually write code for these situations where a single mistake, even a tiny delay, could be absolutely catastrophic? Well, the answer isn't just one thing. It's this mix of raw speed, total control, and a design philosophy that's been battle-tested for decades.
All right, let's set the scene. We're dealing with systems that need two things that often feel like they're pulling in opposite directions. Just unbelievable performance and, at the same time, rock-solid, bulletproof safety.
And this isn't some niche problem, it's everywhere. As of 2024, a whopping 72% of organizations around the world have brought AI into what they do. And if you want to see the most extreme example of this need for speed and safety, you've got to look at high-frequency trading.
This is the world of firms like Citadel and Virtue. Their AI models are making trading decisions in nanoseconds. Seriously, in the time it takes you to blink, thousands of trades have happened and millions of dollars have changed hands. The code has to be faster than humanly possible, and it simply cannot fail.
And, this same kind of pressure is not just about money. It's about lives. The advanced driver assistance system in a car, which is governed by this super strict ISO 26262 standard, has just milliseconds to react to prevent a crash. And an aerospace flight control system, it has to meet a certification level so stringent, DO 178C level A, that it must guarantee stability no matter what. Different fields, but the exact same core challenge.
So, how in the world do you pull this off? Well, let's get into the solution. And it starts not with some fancy feature, but with a fundamental philosophy. C++ is all about giving the developer direct, no-compromises control over the machine itself.
And right at the heart of that philosophy is this really powerful idea with a kind of clunky name, RAII, or Resource Acquisition is Initialization. But forget the jargon for a minute. Just think of it like an ironclad rule for your code. If you grab something, you have to let it go. RAII makes that happen automatically. It brilliantly ties a resource, like a chunk of memory or a file, to an object's life, basically giving it a personal cleanup crew that never ever forgets.
Here's the play-by-play. First, an object is created, and it grabs a resource, opens a file, whatever. Then it goes about its business. Now here's the magic. The second that object isn't needed anymore, like when a function ends, its destructor gets called instantly and automatically, and that destructor's one job is to release the resource. This happens every time, guaranteed, even if some error causes the function to crash halfway through. No more memory leaks, no forgotten files left open. It just works.
So what's the big deal? What does this actually get you? Well, first off, you get automatic, totally predictable cleanup. Memory leaks? A thing of the past. Second, it gives you this incredible built-in safety net, making sure everything is tidied up even when things go wrong. This one idea is the foundation for almost all modern C++ tools that manage memory, keep threads from crashing into each other. It's literally safety by design.
Okay, so RAII has us covered for the small stuff, managing individual resources. But what about the big picture? How do you organize a whole system, like the software for a Mars rover or the entire power grid? For that, you need to zoom out. We need blueprints, or what developers call design patterns.
And this quote from safety engineer Thomas Gebaron, man, it just hits the nail on the head. You need these proven, reusable solutions, these patterns that guarantee your system behaves predictably every single time, but are also flexible enough that you can adapt and upgrade things down the road.
And this isn't just theory, okay? Look at these numbers from the auto industry. One car company found that a staggering 67% of the bugs in their driver assistance software came from just inconsistent architecture. So by putting solid design patterns in place, they cut their critical bugs by 43%. And get this, they reduced safety incidents during self-driving tests by 76%. That's not an improvement, it's a total game changer.
And we're not talking about simple cookie-cutter solutions here. These blueprints get seriously sophisticated. You have things like Clarity, which NASA developed to build software for their Mars rovers that they can reuse again and again. Or Sira, a pattern designed for getting whole teams of robots to work together on a single mission. These aren't just little coding tricks. They're proven strategies for conquering immense complexity.
So we've got our philosophy, and we've got our blueprints.
But even the best architect needs a powerful set of tools to actually build the thing, right? Modern C++ development is all about the ecosystem.
You know, in any of these high-performance systems, one of the biggest questions you're always asking is, where is my code slowing down? Just one tiny, inefficient little function buried deep in the code can bring the whole system to its knees. The answer is a technique called profiling.
And that's where a performance profiler comes in. Think of it like a doctor's stethoscope for your code. It lets you listen in on the final, super-optimized version of your software and tells you exactly what's going on. It'll show you precisely which functions are hogging the most CPU time, and even trace out the hot path, the exact sequence of function calls that's causing the slowdown. It's like getting a perfect X-ray of your code's performance.
And the great thing is, developers aren't starting from scratch. The C++ world is packed with these powerful, battle-tested libraries. You've got Boost, which provides just tons of fundamental tools. You've got Folly, which comes straight from Facebook's high-performance servers. CERN developed Root to handle mind-boggling amounts of data. And of course, NVIDIA's TensorRT is absolutely essential for deploying AI models at top speed.
And that brings us to the final frontier, where things get really wild. We've been using C++ to build these unbelievably complex systems, including AI itself. But now we're starting to use AI to help us write better C++.
Okay, so think about NVIDIA's CUDA platform. It is the undisputed king of the hill for programming GPUs. There are millions and millions of lines of super high-performance code out there written in CUDA. But here's the catch. What if you want to run that code on a different piece of hardware? Trying to translate it by hand is, well, it's basically impossible for any big project. We need a way to make performance portable, automatically.
Now, your first thought might be, hey, just throw an LLM at it. Get AI to translate the code. But it turns out, it's not that simple. Your standard general-purpose LLMs are actually pretty bad at this. And the reason is, they haven't been trained on the right stuff. They don't have that deep, intuitive understanding of what makes this kind of specialized parallel code both correct and, crucially, fast.
But this is where a really brilliant idea comes into play. A new framework called HPC Transcompile. It's a total game changer. Here's how it works. First, it uses an AI compiler to automatically generate thousands of perfect code pairs. One version that's highly optimized for a CUDA GPU, and another that's optimized for a regular CPU. Step 2, it takes this amazing specialized dataset and uses it to train a code-focused LLM. So now step 3, that newly fine-tuned LLM is an expert. It can translate new, complex CUDA code with huge improvements in both performance and correctness. It's literally using AI to create the perfect textbook to teach another AI how to write better, high-performance code.
And that kind of leaves us with this incredible, mind-bending final thought. You know, from controlling every byte of memory with RAII to designing architectures for Mars rovers, C++ has always been the language for tackling the hardest problems we can think of. But as our tools become intelligent partners, as they start writing and optimizing their own code, what impossible challenges are we going to be able to solve next?